Welcome back to my channel. LLMs offer remarkable capabilities, but they demand substantial computational cost. Introducing MiniLLM, a novel knowledge distillation approach that transforms large LLMs into compact models while improving performance in instruction-following tasks. Let's dive in. Knowledge distillation, or KD, is a model compression technique that transfers knowledge from a large teacher model to a smaller student model. There are two types of KD. One is black box KD, where the student learns from only the output text of a closed teacher model, like ChatGPT. The other one is white box KD, where the student has access to output probabilities and hidden layers from the teacher, making learning more precise. MiniLLM focuses on white box KD to build powerful small models. Traditional knowledge distillation minimizes the forward KL divergence between the teacher's output distribution and the student's output distribution. Forward KL works for text classification tasks, but for open-ended text generation tasks like LLMs, the teacher can have many more modes than what the student can express due to limited capabilities. Minimizing forward KLD would force the student to assign unreasonably high probabilities to the very unlikely outputs and generate poor responses during inference. For example, given the input, "Hello, how are you?" a teacher model generates 4 possible responses, each assigned a probability indicating its likelihood according to the teacher. The 4 outputs include one void region, meaning some bizarre response that the teacher model assigns very low probability to. Because of its limited capacity, the student model incorrectly assigned probabilities to the 4 outcomes in the opposite order. The student is penalized the most when it assigns low probability to teacher-approved responses. However, the student is somewhat encouraged for assigning high probability to unlikely responses. Let's try another example. This time the student model spreads out its probability mass, ensuring it covers all bases. In this scenario, the student ends up with a lower KL divergence than before. This happens because, under forward KL divergence, the student model reduces divergence more effectively by avoiding severe underestimation and increasing probabilities in void regions. Instead of forward KL, MiniLLM minimizes reverse KL divergence, flipping the equation. Reverse KL penalizes overestimation, encouraging the student model to focus more on the high-confidence regions of the teacher while assigning lower probabilities to void regions. This means that the student model avoids learning too many long-tail variants in the teacher model's distribution and focuses on the high-confident regions only. MiniLLM's objective is to optimize the reverse KL divergence between the student and teacher models by adjusting the theta of the student model. To optimize this objective, MiniLLM employs the policy gradient theorem. Let's break it down step by step. In a text generation task, the policy is factorized autoregressively, where each token YT is generated based on prior tokens. We then take the log and apply the policy gradient on both sides. Multiplying it by the reward, we get the policy gradient. But what elements should make up the reward function? In knowledge distillation, the reward is defined in terms of the KL divergence between the teacher and student distributions. The per token reward is R, where P is the teacher's output distribution and Q is the student's. The total sequence-level reward RY can be written as a sum of per token rewards. The policy gradient is then updated with RY. Instead of weighting each step equally with the full reward, we replace RY with RT, which is an accumulated reward function from its position onward. We use RT instead of RY because RT ensures that each token's update is based on its future impact, rather than treating all tokens equally. with our T, early token in a long sequence unchanged, stabilizing gradient updates and accelerating convergence. The policy gradient aims to maximize the expected reward J. However, in knowledge distillation, we perform gradient descent, meaning we minimize KL divergence, therefore loss gradient is negative policy gradient. We then substitute J with L and insert a negative sign to the other side of the equation. We subtract 1 from R to stabilize training. However, policy gradient suffers from high variance, reward hacking, and preference over short sentences. Therefore, MiniLLM uses 3 strategies to mitigate these problems. In knowledge distillation for sequence generation, errors in early tokens accumulate, impacting the entire sentence. To address this, single-step decomposition rewrites the gradient into a single-step gradient and long-term gradient. This decomposition reduces variance in gradient estimation, making training more stable and accelerating convergence. The second strategy is teacher-student mixed sampling. During training, reward hacking occurs when the student model only generates the outputs that receive high scores from the teacher. This is especially problematic for smaller student models that exploit weaknesses in the reward function. To mitigate reward hacking, a teacher-student mixed sampling distribution is introduced, where alpha controls how much the teacher distribution influences sampling. This strategy enhances the quality of generations by leveraging the teacher's guidance and alleviates reward hacking. To further reduce reward hacking, MiniLLM modifies the single and long gradients using importance sampling W. However, as W introduces high variance by multiplying per token weights across multiple time steps, it is substituted with a simplified approximation. This step stabilizes training by reducing variance, prevents unnatural, low-quality text generation caused by reward hacking. Because longer sentences cause more variance and potentially reduce overall reward function favors short sentences. The length normalization normalizes reward by the number of time steps in the summation, ensuring that the reward is not biased by the length. Combining the strategies listed above, we have the final optimization gradient, where V is the vocabulary size of the language model. MiniLLM was tested across multiple LM families from 120 million to 7 billion parameters for the student model and 1.5 billion to 13 billion parameters for the teacher model. These models are fine-tuned on instruction-following datasets. MiniLLM outperforms baselines and produces the most precise responses. It provides consistent improvement for both small and large models, and oftentimes outperforms the teacher model. Language generation models suffer from exposure bias, meaning that during inference, student models rely on their own predictions to generate the next token, so small errors compound to large errors over long sequences. For example, during training, when the model is given an input, the capital of France is, the teacher provides the target output, Paris. The student model learns to predict Paris when the input is, the capital of France is. During inference, however, the student model relies on its own previous predictions instead of ground truth. When the student model makes an incorrect prediction, because it never learned to correct its own mistakes during training, small initial errors propagate and distort the output. Unlike forward KL divergence, MiniLLM exposes the student to real inference conditions through teacher-mixed sampling and reverse KL, making it more robust to errors during generation. When using EAE to measure exposure bias, we can see that the EAE of the baselines continuously grow during generation, while MiniLLM has a much lower EAE, and the error stops accumulating when the number of tokens exceed 150. Models trained with policy optimization often suffer from poor calibration, meaning the predicted probabilities do not align with the truth. MiniLLM and baselines were tested on SST2 and BoolQ classification tasks using expected calibration error, or EC. The baselines are worse calibrated than the teacher model, likely because forward KL pushes high probabilities to void regions. In contrast, MiniLLM focuses on high-confidence areas, reducing the calibration. The study examines model performance across different response lengths, showing that all models perform poorly on short responses, as most training data consists of longer responses. However, for longer responses, MiniLLM outperforms baselines in this setting due to its improved handling of complex teacher distributions. Minimizing reverse KL divergence can cause mode collapse, reducing generation diversity. Experimental results show that MiniLLM preserves distinct 4-gram diversity and maintains low language modeling loss. In the ablation analysis, the blue, orange, and green lines represent ablation experiments where one of the 3 stabilization strategy is removed, while the red line represents MiniLLM with all strategies applied. The higher reverse KLD in the blue and green lines compared to the red line confirms that length normalization and single-step decomposition help reduce reverse KLD, improving training stability. The orange line shows a rapid decline in reverse KLD, indicating that teacher-mixed sampling effectively prevents reward hacking. MiniLLM demonstrates superior performance in distilling knowledge from large language models, producing more precise and higher quality responses across various tasks and model sizes. Future work could explore applying MiniLLM to even larger teacher models and investigating its effectiveness in domain-specific applications. If you found this as exciting as we did, don't forget to like and subscribe. Thanks for watching, and we'll see you in the next video.